maybe? Okay. All right. So we're talking about buffers today. So I'm hoping that we're at the point where you guys are comfortable enough with using terms like I'm going to be saying the weak acid and the conjugate base and adding a strong acid and stuff like that, because I could tell in my last class I was nervous that people were not following, not because they didn't understand the basics that I was talking about, but because of just like regular acid-base terminology. So hopefully by doing the homework last night, you've gotten comfortable enough with that, comfortable enough with some of the simpler calculations like doing pHs and pKa's and stuff like that, simple ice tables, that we can move into this and kind of build on that a little bit. Okay, so we will probably come back to these notes, but they might just be useful for you to refer back to, these overview notes. We want to talk about, in this one, since it already has this particular buffer solution here, I'm going to go ahead and use this. Before we get started, I'm going to write out the equation, the Ka equation, so the acetic acid acting as an acid in water. Okay, so let's start just if we had acetic acid. Let's think about just that, like what we did in chapter 17. We added 1 molar acetic acid, right? And we could calculate the pH of that if we knew the Ka, which is 1.8 times 10 to the negative fifth. We could take a concentration of acetic acid and calculate the pH. This is a very reactant-favored reaction, though. The reactants are primarily the thing that you're going to keep. You're going to have a very small amount of product. So when we start talking about buffers, which think of buffer just like you would use it in everyday conversation, it like prevents something from affecting something very strongly, right? Like you can buffer sound, you can buffer light, I guess. You don't really use it. The sound is like the most obvious one to me, right? You can like put up insulation or something and buffer noise. You can close the door and buffer the noise. So a buffer in acid base is something that can buffer the pH. So it reduces dramatic changes in pH. When you have a buffer, you can't just add a weak acid. If you were to just add a weak acid, it would have some of the conjugate base, but because it's very reactant favored, you'd only get a really small amount of the conjugate base. And when we make a buffer, we actually are aiming to have similar amounts of conjugate base and acid. So the way that we do that, there's actually 2 ways, but kind of the more traditional way is that you add both the acid and the conjugate base into a mixture. So you're starting with both of these things, but you're starting with them by adding them in. You're not like letting the acid come to equilibrium, okay? So maybe you add 0.1 molar of the acid, but you also add 0.1 molar of the base. Okay, so that's the first step. I'm going to use this picture to talk through what it means when we say it buffers it and how it works. So let's pretend we do just the amounts we started with. 0.1 molar of both the acetic acid, so that's our HA, and the acetate ion, the A minus. Okay, so we start off with the same amounts. And like, let's think about if we just had water and we added some acid. Obviously, that's going to change the pH, and probably significantly if it's a strong acid and there's a decent amount of it. If we add a base, it's also going to change the pH, and it'll increase it, make it more alkaline. If we have a buffer, instead of reacting in the water immediately, that's strong acid or base, it actually will react with, if it's an acid, it'll react with the conjugate base. And if it's a base, it'll react with the conjugate acid. So I hate that I used two different examples here. We're going to just use the one we have above, okay? So I want to start by writing what happens when we add acid to this system of acid and conjugate base, and then what happens when we add base to the system. And then we'll talk about how we can look at it with Le Chatelier's principle. So the first one, we're going to add acid to the system. The second one, we're going to add base. Okay, so like I showed in the picture, and we'll go back to that picture in a second, if you add acid, and when I write H3O plus and OH minus, I mean we added a strong acid that immediately got converted to H3O plus, okay? But if you have another base in the presence of that H3O plus, it will react with it. So if I have the acetate ion, see, how do we write that up here? C2H3O2. It will actually react with the acid and convert some of that conjugate base back to the weak acid. So it won't just sit there, is the point. If you have a weak acid and its conjugate base, you add an acid to it, the acid doesn't just sit there and affect the pH, it will actually react with that conjugate base that's in the container in the solution already. So if we added this by itself, we would measure it and it would change the pH. Instead, it reacts with this guy and produces that, which this does have a little bit of an acidic effect, but it's much less than the strong acid itself. We'll do calculations of this and show you how this happens so that you believe me that it changes the pH, it just doesn't change it nearly as dramatically. Okay, if we have a base, it's going to react with the weak acid. So it would mix with the acetic acid and produce acetate ion. So again, instead of the OH minus just sitting there and being measured and affecting the pH, it reacts with the acid and produces some of the conjugate base. Yes, this will affect the pH, but it's a weak base, right? So it's going to affect the pH only a tiny bit compared to if the OH was just left there in the solution. Okay, so back to this picture. If we add acid, it reacts with A minus. So A minus decreases a little bit because they're combining, and it makes HA. It makes some of that acetic acid, right? So instead of it just sitting there, it reacts, uses up some of this, makes some more of that. If we add base, these two are going to react, uses up some of that, and makes more of this one. So the key point is it has something to react with. The acid or the base, when you put it in there, it has something to react with instead of just sitting there and having an effect on the pH. This is also one of the reasons why when we first make these, we want them to have usually close to equal amounts of each other. So we want 0.1 molar of the HA and 0.1 molar of the A minus, because anytime, if we tried to keep adding acid, we would keep depleting this A minus and making more and more of the HA. And eventually we'd run out of the A-, right? So we want to have lots of that to react with, but we don't know, are we going to add H plus or are we going to add OH minus? So we want lots of the two components. That's another thing I'll circle in a second. We want as much of it as possible. So it would be even better if we could have 0.5 molar or 0.8 molar or 1 molar, because we'd have lots of molecules to react. And then we want them in equal concentration so that we can go either direction. We can react with either one and add buffer on the acid side or the base side. Okay, I know I'm jumping around a little bit. So I'm going to highlight the key things that we like buffers to look like. We want more of them, like higher concentrations, and we want similar amounts of both the acid and the base. Okay, the last thing is, what pH are we trying to keep this solution at? Because there might be instances where we want it like totally neutral. That's the case in blood. I think it's like 7.2 is like optimum blood pH. But there might be other instances where we want it to stay acidic. We just don't want it to be too acidic or too basic, but we want it to stay at a low pH, okay? So what we do with buffers is we pick a weak acid that has a pKa. Remember, P is just negative log of the Ka. It has a pKa similar to the pH we're looking for. So I Googled this in my other class. I want to Google it with pKa table. Okay, this is not a normal. I don't know why it came up with all these. Oh, because in organic we use lots of pKa's for some reason. Okay, whatever. We'll just look at them. Okay, so, all right, so let's say that we want one, this is terrible, but let's say that we want one that is slightly basic, okay? We want it like 8 or 9 or something like that. We would look, I gotta find a better one. This is gonna drive me crazy. Not organic, something not organic. In my other class, I just looked up Ka's and it was just fine. But I wanted you guys to see pKa's because that's what we really care about. But apparently that's not going to work. Ooh, look, look! Yay! Okay, found exactly what we wanted. Okay, here's the acid. And here's the Ka, and then there's the pKa. Remember, all you have to do is take the negative log of this, and that'll give you the pKa. You can get a general feel for it by just looking at the exponent. So I know that's really blurry, but like 10 to the negative 4th, that's going to be around 4, okay, 3.75. 10 to the negative 7th, that's going to be around 7, 6.37, okay? So if we have a desired pH, like, this is an interesting one. I just said blood pH was 7.2. Phosphoric acid would actually be a decent buffer in our blood because it has a pKa of 7.2. Carbonic acid is actually the one that gets used the most, and that's because it's carbon dioxide combined with water. So it's something that's in our body a lot of the time anyway. I guess we have loss of phosphates too, like ATP and ADP. Anyway, if you wanted a really acidic buffer, so you were looking for something with a very low pH, but that still buffered changes in pH, you'd be looking up here, pKa's that were, 1, 2, 3. Okay, so that's the last thing, is that whatever pH you're looking for, you want it to be close to the pKa. Okay, so there's two types of calculations that we're going to do with buffers. One, we're going to calculate the pH of the buffer as is. It will be close to the pKa, but it kind of depends on how much of each of the components you have, like the ratio of the acid to the conjugate base. And then we're going to look at what happens when we add the strong acid or strong base. How does that change the pH? Okay, and we'll see that there are slight changes, but they're not super dramatic changes to the pH. So let's go ahead and do one of these first ones. And we are going to ignore this thing that says the ice table, and I'll tell you why in a second. Or maybe I'll do it with you, and we'll see that we get the same answer. Okay, so there is this equation called the Henderson-Hasselbalch equation, and it's used specifically for buffers, and it's fine to use any time you have that small k that allows you to ignore x. All right, so if the k is less than or equal to 10 to the negative fourth, then you can use this equation. And I'm only going to do buffer problems where we can use this equation, but I want you to make sure you know when it's appropriate. So pH, it's on that previous slide too, but I'm going to rewrite it here. pH equals pKa plus the log of the concentration of base over the concentration of acid. Base meaning like the conjugate base. So that is actually a summary of how you would do an ice table when the K is small, believe it or not. So what I want you guys to do is use that equation and solve for the pH of this buffer system. And then I'm going to do an ice table to prove to you that it's the same thing. Okay? So use the Henderson-Hasselbalch equation to solve the pH of this system, this buffer system. Okay, so you don't need to copy down the whole ice table if you don't want to. I'm just proving it to you that the equation works the same. There they go again. All right, did anybody get 4.64?
I got 4.8.
Did you do base over acid? So the base is 0.2 and the acid is 0.25.
No, I did acid.
Okay. A way you can check yourself is the base is in slightly higher of a concentration. So you should expect the pH to be slightly lower than the pKa. Because if they're equal amounts, then the pH would be equal to the pKa. But if they're slightly more acid, it should go slightly lower, slightly more acidic.
What did you plug in for pKa?
Negative, it should be 4.74, I think. So Ka is 1.8, so negative log of 1.8 times 10 to the negative fifth, which I believe is 4.74. You guys can correct me on that if I'm remembering it wrong. There's no water in there. So if you had 0.25 of both of those, it would be log of 0.25 over 0.25, which is the log of 1, which is equal to 0, which is why if they're in equal amounts, the pH would be equal to the pKa.
Yeah, I got
Okay, so as long as, if you were to do an ice table and you could ignore the minus x and plus x, that's when it's okay to use Henderson-Hasselbalch, which we will always do buffers where we can use that, but I just want you to know, like, you know, sometimes I have concept questions on there, like, is this system, you know, could you appropriately use the Henderson-Hasselbalch equation here? Otherwise, we would have to do the whole ice table, we would have to do the quadratic formula, and it would be a lot more involved. Okay, let's do one more of these before we add anything else to the buffer system. Okay, so this one is a different system, and it actually gives us the KB. Now, you could go ahead and do this with a KB. You'd probably just use an ice table, but the easier way to do it is to remember KW equals KA times KB. Okay? I'm not going to point it out to you right away, but realize this question is a little bit different. It's not asking you to calculate pH. So go ahead and take a few minutes to work through this one. Talk to your neighbors if you're like, I don't even understand what it's asking. Was that in here where I was talking about struggling with it and I said about somebody who couldn't find their shoes?
Yeah.
Same thing this morning. They're going camping this evening, which is stupid because it's totally raining, but whatever. And he's like, I can't find my backpack, Mom. I can't find that other backpack. It was hanging on the end of his bed. Like he's digging through his closet. I don't understand.
Does he have glasses?
No, does he have glasses? No, he's just 9. They just don't look very hard on their own.
Does he have glasses?
Here's Gaia today. And she looks back at Jenny and she goes, Jenny, what is your clan doing? Jenny's clan, from my perspective, is perfectly fine. Jenny, I don't know what. God, never mind, I'm just one. Sometimes she doesn't make me. She's just wonderful. I'll ask her. I was like, what does the official say? She's like, I don't know.
How do you think
I
people
do
walk
understand.
certificate?
So,
You raise
so
the
basic
power.
he's given. Okay, so you're trying from this equation, you're trying to find a K, right? And then we're trying to KA.
Fucking mercy,
And
we
that's
surface
the
area.
negative log.
Mercy.
Okay.
Oh, we found out yesterday. Remember how my freak out teacher
KV.
disappeared?
KW is a
No, she didn't
constant.
die. She's retired.
Oh, and then negative 14.
I was kind of scared whenever she was like, I have a message about Shirley being. Did she? She retired.
She just decided about it like right in the middle of the semester.
Well, I'm sure that like there was some like driving force that kind of pushed it. It was actually specifically our class. Remember I remember when I told you that she's like, no. She said that she threatened the head of the math department that she was going to quit. Because of our class. Because she couldn't figure out how to work the fucking book that she signed up for.
This is the legal process. I don't have it. What is the file for this file? Slash, do you, she's just gonna give us a test before?
No, this test is during the final stuff. We wouldn't have it during final, it's just this stuff.
Okay.
It's either Thursday to 11 or I have to I don't think it's Thursday.
Okay, did we figure out what it's asking for?
The
It's
concentration,
Thursday 10:30.
like the acid to base concentration ratio.
Yes, the acid to base concentration ratio. So it's looking for this part of the equation, acid over base. No, other way around.
Base over acid. Sorry, I messed you up.
Yeah, it's your fault. Okay, base over acid. So like if it comes out as 2, that would mean you want 2 molar base and 1 molar acid, or 1 molar base and 0.5 molar acid. So I'm going to replace that ratio with X. So I'll go ahead and work it up here. If you're not done yet, that's fine. Keep working. Or if you're lost, you can watch me do it up here.
I mean, yeah, it's scarred. It's not gonna get away. It wasn't like I just like freaking touched the hot. My arm was there for a minute. Because when everything's just so light, you don't register it right away. Like it's just like. Like I still have this scar. This is from shaving my arms. And I was like, I don't know.
Did you guys finish already?
Yeah,
Okay.
I'm done.
Lily. Oh, okay. Did you get 0.4? Oh, yes, that's what I mean. No, it was 0.04 and then it was 0.4. That would be right, right? Nah.
Wait, what
Hold
is-
on.
The I got as my final answer. Point,
I didn't.
I got 0.398107.
Well, that's 0.4.
Yeah.
Yeah, okay. I think the only thing I don't remember if I did right was this part. Hang on, now I gotta check my work. I was just remembering from my previous class, and sometimes that's not always reliable.
I don't know how you got the answer.
I just don't know why the math works out there. That's okay though.
For what step?
It's okay. When you do 10 to the negative 0.4, shouldn't that be?
Yeah, I got 0.398.
It just doesn't feel, I know it's right. It just doesn't feel right.
Because I got 9.
Okay. Do you want to walk us? That's not right, but do you want to walk us through?
No, I didn't.
I mean,
It still bothers me.
my calculator doesn't go back.
So when you do logs, when you're undoing logs, you need to do 10 raised to that.
Yeah,
So did you get to this point here?
I got to the step above it. I had 10.24.
Minus 10.2, 10.64.
Oh, okay.
Okay.
I got it. Thank you. I divided.
That's okay. I did an acid-base ratio in the other class where I added them instead of did one over the other. And I didn't even realize it until I just looked back to my calculator.
Mama did this work.
It just still bothers me that 10 to the negative 0.4
It's still point.
is still 0.4.
Yeah.
That doesn't seem right to me for some reason. It's fine. But like it makes sense because 4 times 10 to the negative 1, that's what 0.4 is.
Hold on.
So the log of that, 4 times 10 to the negative 1. Yeah, the log of that should be 0.4. It just, it's fine. I can't argue with math.
I think it's just like a weird like point because if you do 10 to the negative 0.5, it's 0.316. Then if you do 10 to the negative,
Oh, it's like some weird midpoint or something. That's fascinating. Okay, that actually makes me feel better. It was an anomaly. Okay, so what does this mean? It means that I need 0.4 molar base. What was the formula? CH3NH2. That is the base. For every 1 molar CH3NH3. So when you get just a regular number like that, so I would probably phrase it in the answer as something similar to this, just to be very clear. You know, that's still 0.4, right? 0.4 over 1. Okay, so the last thing we're gonna do is and then we'll do all of these on Monday. We'll be practicing these, but we're gonna do one problem together where we look at how adding acid, I think it is, affects the pH. So like we're gonna look, I'll give you the starting pH and then we'll go through the steps that you would do because this is just the buffer itself. This is like you made the buffer. You haven't done anything to it. You haven't like stressed the system. The fact that I just used that word reminded me that we didn't really talk about this in terms of Le Chatelier's. So what we're doing now is we are going to add acid to a buffer solution. So the purple is what we're doing. We're adding some acid, right? So Le Chatelier's tells us that if you've got a system in equilibrium, which is really what we have right now, we have the acid and conjugate base. We added both of them, but they still have to achieve an equilibrium. We just started with amounts of both of them. You can also look at it down here where I did the calculation. It would look kind of like this, right? We started with amounts of both of them. They're in equilibrium, and then we add some acid to that system. Okay? So Le Chatelier's tells us that the reaction will shift in this direction, which is just what we saw in the picture too. We use some H3O plus, we use some of the conjugate base, and we make some of the original weak acid. So the green is kind of how the system responds. It shifts towards the reactants. So this is a really good way of thinking about how buffers work. It's just that if you're thinking of the Ka reaction, Then if you add base, that's like dropping the H3O plus, so it shifts towards products. It's weird because OH minus and H3O plus are inherently tied to each other in water. So like if you talk about adding base, you can also talk about that as a decrease in H3O plus. So we described it as like two different reactions, which is true, but it's also well described by like a shift in the equilibrium that's in that system already. So that's what we're going to do now, is we're going to do the purple thing. We're going to add some acid, and we're going to see what happens to the pH.
Whenever you make a buffer, is it adding something else to water, or are you adding two separate?
You're adding two things to water. Now, technically, you could add like a weak acid and then a little bit of strong base, basically to convert some of it to the conjugate base. But in the end, you want the two things and just those two things to start with.
Okay.
Yeah. Okay, so there's these three steps we're going to go through anytime we have a buffer system. And these are the same steps we'll do with titrations, which is the stuff we'll do Wednesday and Friday of next week. So when we do these, we're going to have these three main steps. I'm going to call the first one dilution, the second consumption, and the third equilibrium. Now, the first one, in this next problem we're going to do, we don't technically have to do a dilution. They made it easier for us. They just said you add a certain number of moles. So you will have to calculate a molarity, but you don't have to consider a dilution. When we get to titrations, for sure, you're going to be mixing two liquids. So you're going to be increasing the volume. It'll be like you start with 25 mils of acid or buffer or whatever, and then you add 5 mils of something else. Well, now your molarity just changed because you had 25 mils and now you have 30 mils. So you're going to have to account for that before you do anything. The second step, consumption, is basically just, I treat it kind of like an ice table, but we know what the change is because it's a strong acid basically that's going to push all the way towards products. And then in the equilibrium step, we're really just going to use the Henderson-Hasselbalch equation. So you don't even have to worry about the ice table. Okay. So 0.005 moles of HCl is added to 250 mils of this existing buffer solution. So they're in equal concentrations, the acid and conjugate base. And we're dealing with molarities here. So like if they already told us the molarity, as long as we don't add any additional volume, that's fine. We don't have to change those. We didn't add anything. We already had 250 mils, but it said we added 0.005 moles of HCl. This is kind of dumb because HCl doesn't come in a solid, so like this would be virtually impossible to do as without increasing the volume, but we're just trying to simplify things. So we are going to have to calculate a new molarity for HCl, not a new one, but a molarity. So just like we've done this whole time, moles over liters. What is that? Is that 0.42? It's like a weird repeating number today. No, it's 0.02. Okay. Okay, so now we have the molarity of the HCl. So we should be able to just use those molarity values now to do this. Okay, the question doesn't ask for this, but I want to just real quick so we can compare things. I want to calculate the original pH of this system. So before we've added anything else. So that's just the Henderson-Hasselbalch equation. And it's really easy. Oh, I did it again. Base over acid. This one's really easy because they're both 0.25 molar. Okay, so pKa we said was 4.74 plus the log of 0.25 over 0.25. If you do the log of 1, it'll be 0. So the original pH is 4.74. It's equal to the pKa. Maybe I'll pop that up at the top here so that we have a little more room. Okay, so that's our original pH of this buffer solution. Now we're gonna add the acid and we wanna know what the new pH is. So we kind of did, you can count this as step 1. It's not really a dilution, but we calculated the molarity. Now we're gonna do this consumption step, like consuming that acid. So the acid is gonna react with the conjugate base. So I'm gonna write an equation for that. And instead of writing HCl, anytime I have a strong acid, I'm gonna write it as H3O plus, and anytime I have a strong base, I'm just gonna write it as OH minus. Because we know that whole 0.02 molar HCl turned into 0.02 molar H3O plus immediately, because it was a strong acid. Okay, so that's the equation for my consumption step. The buffer told us that both the acid and conjugate base started as 0.25. And then we added 0.02 of the acid. So I set this up like an ice table. I just call it, shouldn't even be called final. It should be like called middle or something. Because this isn't the equilibrium. This is like the values we're gonna put into the Henderson-Hasselbalch, which is doing the equilibrium. I actually like it better when we do an ice table, because then it's like ICF, ICE, and it's like two of the exact same things, same approaches. Okay, they're not that similar, never mind. It just is like a same way of solving it. Okay, so in the change here, we don't do a minus X. This is a full arrow to the right because it's a strong acid, so we consume all of the acid or base. Okay, so I'm gonna subtract 0.02 off of each of these and then add 0.02 to the product, because I want my final to have none of the strong acid or strong base at the end. So all I've really done now, just like the picture from the beginning, I've changed the ratio of weak acid to conjugate base. It used to be a 1-to-1 ratio, and now it's 0.27 to 0.23, or 0.23 to 0.27. So that's my step 2, my consumption step. And now my last step, the equilibrium, I'm going to use the Henderson-Hasselbalch equation again. But this time I'm putting in these new concentrations. So 0.23 and 0.27. I want to do that in my head. Six, 7. So it dropped the pH a little bit, 4.74 to 4.67. If I had added 0.005 or 0.02 molar H3O plus to water, it would have a pH of 1.7. Okay, so the buffer did a whole lot. It took it and only let it drop less than 0.1 pH units instead of dropping it basically from 7 all the way down to 1.7. Okay, so it has a huge effect on, what is another word for buffering? For, it has a huge effect on not allowing that strong acid to do damage to the pH. Okay? All right, so Monday will be all practice problems of stuff like this, and then we'll apply it to titrations on Wednesday and Friday. And then that will be the end. Are you gonna cry? You're gonna cry, Olivia, aren't
It's
you?
just like scary. Like, what do you mean it's done? Like it's just weird.
I know.
Like, it went by really fast.
You can always teach
Yeah, you want to pick up an extra section of OChem so that way I can fit it in my schedule?
No. No, thank you. Every once in a while, I think it'd be kind of fun to do that, but it would be so much work.
Well, next semester is the golden opportunity.
We won't make it hard.
You don't even have like hardly any chemistry to do this weekend. We just barely started a new chapter, so you can't really do a whole lot of homework. And you just finished a chapter. You should like ignore chemistry for the weekend.
I just got an email that says Trump versus science, and I'm a little bit scared to open it.
I mean, that's been going on for like the last decade,
Yeah, I did see
so.
that.
Did you see Bill Nye?
No.